up as the presenter. So I will do my best, but I have to be honest with you. This is a very preliminary idea that we discussed, and he put that on paper and submitted. So this is going to seem this is actually quite simple, but I hope it generates a little bit of discussion. The idea is the analysis of the load growth direction variation in the dynamic security assessment. The slide. And, well, quick outline of the presentation that I'm going to skip because of the time. So voltage stability assessment is obviously important for several reasons. Most of them were already discussed here. Usual index for voltage stability assessment is the voltage stability margin. So we've talked about that. I've shown you the concept of voltage stability margin in my previous presentation. But this stability margin is a function of the defined load growth. And actually, the direction of the generation growth also matters for calculating the voltage stability margin. So if an operator knows precisely the direction of load and generation growth, then the voltage stability margin is of practical significance. However, if there is too much uncertainty on this parameter, on this information, then you may get poorly reliable voltage stability margin. And then this work presents a modeling that incorporates some sort of very, very crude extensive calculation analysis to include the variation of the load growth direction based on dividing the system into several areas and assigning participation factors for these areas, and then compute the stability margin. Well, we start with the load parameter, which is to compute the PV curve, as Glauco has shown us at the beginning of his presentation. We have the load parameter, and it can be the varying parameter for the calculation of the PV curve. We have the total active power consumed by the loads divided by the same amount in the current operating condition. So we define the load growth direction as a sum of participation factors from areas here, which in turn will be a sum of participation factors of each bus. And this can be measured, for example, by synchrophasors. And then, if we have this information, we can calculate the participation factor of the ith area by this formula, where this factor gamma, PA here, is calculated by this expression. And in the calculation of the participation factors of the areas, we have the participation factors of the buses, so they are defined in a similar fashion. So this is basically a very simple idea of splitting the system into several areas and to make the computation, to diminish the computational burden. Then the areas will be represented by their respective participation factors. So this is the definition of the load growth direction. It involves all these parameters. And the generation growth also matters. So for this, this work, we redispatched the generators based on their inertias. And so here's the algorithm for the calculation. Obtain the parameters, all the parameters required to calculate the power flow, define, split the system into areas and assign the participation factors, define these participation factors, and scan range of participation factors for each area. So in this case, if you scan the participation factors of the area, increasing one and decreasing another, you get some kind of uncertain, or you insert the uncertainty in the calculation of the voltage stability margin. And so you increase the participation factors until the upper limit is reached, and then you will have the final result. This is the case study. The analysis was performed in a reduced model of the southeast Brazilian system. And here is what we get. If we compare, if we plot the stability margin for different values of the participation factor of area 1 against area 3, so you can see that the participation factors are scanned from a value from 0.2 to 1 for both areas. And what you see in this surface here is the stability margin, which is evaluated according to this scale here, right? So the idea is that you split the system into areas, you scan the possible participation factor of these areas in the load growth direction, and then you get several possibilities here to come up with the possible load growth directions and their respective impact on the stability margin. The same can be shown for area 2 against area 3. So very similar plot with a few differences. But the conclusion is that the load growth direction variations affect the system, the voltage stability margin, and this has to be studied. This is a first step towards this objective. And future work includes developing an approach to estimate the load growth direction in real time using PMU data, which Glauco has shown us before. So I'd like to acknowledge University of São Paulo, FAPESP, and CAPES for the financial support to this work. This I conclude my presentation. Thank you.
Thank you, Rodrigo, for keeping the time. Please, questions for Rodrigo? Kleber?
Congratulations. Thank you for your presentation. Do you think it's important to take into account kind of generation growth direction, something like that, because in this work you only evaluate the load growth direction. What about the penetration level, for example, of GD?
Well, thank you for the question. It's indeed, it is very important because the voltage instability phenomenon is related to one or more lines of the system exceeding its transfer capacity. So it will obviously depend on the load growth direction, but the way you redispatch generation to match this load is another factor that is very important to calculate a reliable voltage stability margin. So this was a very preliminary approach. We redispatch based on inertia, but we, in the sequence of this research, we want to model more realistic redispatch approaches.
We have time for one more question. Yes, I have one. How you compare your proposal with regular nomograms that they try a lot of directions? So how would your work would fit in the nomogram DSA?
Thank you, Glauco. That also gives me the opportunity to make an explanation because I have, because of the time, I just quickly mentioned that update the differential algebraic equation of the power system. So that means we are working with short-term voltage stability again. It's not, so this is the basic difference with the nomogram approach. Here we investigated this effect on the short-term voltage instability.
Okay, let's give another round of applause to Rodrigo. So I invite next speaker, Mr. Rosvando. Is Rosvando here? Yes. Okay. Rosvando did his engineering, electronic engineering, right? From Unifei, Itajubá. And he's currently a master student at USP São Carlos, correct? Okay. You have 10 minutes, please. Try to keep strictly.
Thanks. Support, okay?
Then you can use this.
Okay. Good afternoon. My name is Rosvando Júnior. I am a master student at University of São Paulo in São Carlos, same the Professor Rodrigo. And the group presented this work, one embedded state estimator for reducing data volume and the process in smart grid monitoring. The presentation is structured as follows: introduction by case study, basic concept, smart grid and communication networks, the proposed embedded state estimator, results and simulations, and conclusions. The monitoring power system is fundamental to contingency analysis, preventive and corrective control, and network security. This mainly in the area of the generation and transmission, because the advanced use of the supervisor system SCADA. But what is to monitor in real time all power system? It's meet the current operational state of the all the bus. Of the main tool for this is state estimator. This fornecing, consisting in obtaining the nodal voltage complex. Recent events occurring in distribution systems, among them development of the so-called micro PMUs, phasor measurement units, and installation of smart meters in the low voltage distribution networks. This is process of the state estimation, where Z is the measurement vector, X is the state variables vector, H is the set of nonlinear equations that relates the measurement with the state variables, and E is measurement noise vector. The several methods were developed to perform the process state estimation from the classical rate to least squares. From the objective is defined the n vector x that minimize the index j present allows, and the Jacobian matrices and the gain matrices. This equation is used to evaluate the computational burden of the system, where n is the number of state variables, and calculating flows. Smart grids aims to modify to power grid to a powerful and reliable system, incorporating several automated control functions. The advanced measurement infrastructure contains smart meters installed in low voltage networks. AMIs use three types of communication networks generally: general packet radio servers, or global system mobile, power line communication, and the radio frequency. This is the proposed embedded state estimator, where the three aspects must be taken into account for AMI projects: data volume, communication requirements, and processing capabilities. In the figure, it shows the any parameters input and output for the embedded state estimator. By example, logical device measures its connectors and measures from the micro PMUs, electrical measures from smart meters, network configurations, and the others. The parameter of output, the ESE, is it's a result of state estimation process, variables of from tire bus, and others that's choose for the GOC. Here, illustration of the embedded estimation implementation is shown. Based on above, the following 6 ESE deployment scenarios were evaluated. 1. Installation of an embedded estimation for its distribution transformer. 2. 500 meter range for embedded estimator. 3. 750 meters range for each embedded estimator. 1,000 meter range for each embedded estimator. And installation of one embedded estimator for each distribution feeder, and complete network sending data directly to distribution operation center. This is a system using a case study from the city of Londrina. The first step was to separate consumers to its scenarios defined above, where the smart meter sends other package of conventional 3,185 bytes per day, while the amount of information received some 272 bytes in the same period of time. This table presents the computational burden required for Raspberry Pi is used in study case. When that's it's possible to observe the rise exponential of a number of points in operations. This scenario represents the centralized approach, where the whole city of London is connected to AME project, and where monthly 28 gigabytes, weekly close to 70 gigabytes, and daily close to 1 gigabyte. The data volume reduction with embedded state estimator is present in the table. It's clear the significant reduction of process memory and bandwidth required for the real-time operation of the distribution system due to use of embedded systems. Amount of data to be processed by ESE for each distribution transformer per day is presented in figure. The outliers represent the transformer with more connections in low voltage networks. Its conclusions. Given the increasing technological challenge required by smart grids, it's necessary to improve the way utilities manage information for electrical networks. For all the SA deployment scenarios, however, have a considerable reduction is noted in amount to data to be transmitted and processed to perform state estimation. And in addition of allowing the reduction information traffic, to use the proposed ESA in decentralized also allows operation cost reduction. This is reference used in the work. Thanks.
Okay, questions for Osvaldo? Okay. You have shown us that this new paradigm of state estimation and distribution, it's an area that data builds up very fast due to the capillarity of the distribution, right? And how far is the technological to the application? How do you see how willing the distribution companies, let me say, willing to put the technology in field? Do you have an answer for this?
How to technology use it? For
how are the distribution companies willing to do that in Brazil? If you know, if you don't know, just say don't know.
I study of cases of implantation of smart cities Aparecida do Norte, of Cepel, and
Parintins.
I don't know this. No. And another piloto projects installed in the Eletronorte in Presidente Prudente. The same Copel in Londrina, the project of one smart city, the base for study.
Okay. Okay. Rodrigo, question? Mas você responde aqui.
Oh, there's always the guy who is going to make more of a comment than a question in any conference, right? So it's more of a comment than a question. But just you mentioned pilot projects. It's still incipient in Brazil, but we will have a talk by Professor Valmir Freitas about this one pilot project by CPFL, which is a utility in the Campinas area, and the district in Barão Geraldo is moving towards this ultimate goal, which is state estimation and the distribution. So it's just to add on the response of Osvaldo.
And we are going to have more of that tomorrow, right?
Yes, yes.
From
Valmir.
Yes. Okay. Thanks, Rodrigo. Let's give another round of applause to Osvaldo. So, at last but not at least, I call Tiago Honorato to come up here. Tiago not just graduated, he graduated from UNB in 2016. And now he's a master's student here at UNB. Is Kleber a student? No. Okay. Yes, Kleber is co-author. 10 minutes, please.
Okay, so good afternoon, everyone. My name is Thiago. I'm a master's student here at university. And as the title implies, we are proposing here is a phasor estimation algorithm and based on half-cycle DFT. So just a brief contextualization for those who are not familiar with phasor estimation. Phasor estimation is basically a sinusoidal signal phasor representation. So that's basically it. And just simplifying the process inside the relay, we will have our CTs and PTs analog signals, and we have a sampling process. And after that, we will have our phasor estimation. And the output of phasor estimation goes inside the protective relay algorithm, right? And it's based on fundamental frequency. And regarding half cycle algorithms, not many can be found when we compare to full cycle ones. And I mean, due to the speed that they can provide, it could help in system stability and as well as equipment damage. So one question that may arise is why study phasor estimation? You know, and it's simply because it can be influenced by a couple of factors like harmonics, decay in DC component, as well as CT saturation, just to mention a few. And in this study here, we focus on decay in DC component. So our objective here is to combine an efficient decay in DC component elimination with modification of a half-cycle discrete Fourier transform, as I mentioned in the beginning of the presentation. So to do that, we use a decimation process in parallel with odd and even sample separation. I think that will be clarified here in the future. So, and we compare our response with others algorithms in the literature. We compare with Hroslovsky and Shane. So, going a little bit on phasor estimation here, just so we can clarify a couple points. So there's a typo here. So it should have been, it's not sampling window, it's moving window, okay? So just to clarify that. So we have animation here. So there's our moving window. So when we estimate a phasor, we have a window that has a constant number of samples. And this window moves every time there's a new sample, okay? So there you can see a moving window, right? It started here, and then it goes moving throughout the signal. And here I show a little bit about the Fourier algorithms. So we have full cycle and half cycle. I'm not going into the nitty-gritty, you know, the details, if you will, of the formulation itself. But that's basically how you calculate it. You have a real part as a result of that, and as well as an imaginary part. So you have a phase, right? So our focus here is more on the half cycle formulation, right? Because basically you want to modify it. So just a little bit of comment here on the decay indice component. So as you can see, it has quite a rough effect here on the phasor estimation, especially on the half cycle version. It has a lot of oscillation, and that can really impact the algorithm response, right, in the protection relay. So now going into the proposed algorithm, as I mentioned again, it's a modification of the half cycle version of Fourier's algorithm. And first thing is, I need to clarify his odd and even sample separation, right? So if we record a signal there, already sampled, and I sample at 16 samples per cycle, we have here our window with 8 samples. So as you can see there. So all we do here, we do a decimation. So we decimate by 2. So but what do that mean? That means that we're getting samples 2, 4, 6, and 8, applying the FCDFT. Actually, there's a typo again. It should be 8 CDFT, right, from half cycle, sorry. So 8 CDFT, and then we get these 2 phasors here. I mean, this one phasor, this real imaginary part here. Even, and decimated by 2. Then we get the same thing with the odd samples. So we get 1, 2, 3, and 7 samples. Then we apply it again, the FCDFT. Again, a typo here. And we get this odd decimated by 2. And then we do it again, now by 4. So repeating the process, but decimated by 4. We get 4 and 8 samples, and uneven samples, and then 3 and 7 odd samples. We apply the filter again. Then we get this other phasor there. Then I won't put everything here, the formulation, because it's quite extensive and probably will take a lot of 10 minutes to explain all of that. But all we can do with that is just calculate this lambda. And then after calculating the lambda, we can apply this expression here with A and B being this formulation here. And the delta is 2 pi over n being the number of samples. So after that, we can calculate the real and imaginary parts here, the phasor, without the decay indice component. So to evaluate the performance here, we have our test system and the semi-anti-based test system. So basically, we have here is an equivalent on this side, on bus L, an equivalent on that side, bus R, and a transmission line here. So it's a 230 kV system. It's 100 kilometers transmission line, perfect transposed, and modeled as frequency constant distributed components. And the model of the CT that we use. The CT is not represented here, but I mean that's what we use. So going through the results here, we can see that I don't know if you guys can see properly, you know, the colors. I'm not sure, but so this one is the Hroslovsky, and this other one is Shane, and that's ours here. So you can see that it doesn't have any overshoot. You know, it's very smooth, even though it's a little bit behind. You know, there's a little bit of delay here. going on. And that's a B phase for a BC fault at 10 kilometers. Next signal here, we have phase A of AG fault at 50 kilometers. And that's from terminal L, I think, from the system. And very similar results here. You know, Rosolovsky has a lot of overshoot. And then we have Shane, a little bit smaller overshoot there. And then we apply a test signal. So the test signal is we use to emulate a second decaying DC component. Like it could come from CT saturation. Right? So another time, we use these parameters here to consider the decaying DC components. And then that's what we get. Another time, very smooth response. And for the second signal, pretty much the same thing. And conclusion. So Pro's algorithm provides effective decaying DC component elimination, as we could see from the results. It has a smoother response and lowest overshoot from the test algorithms, as we just shown. And this is an important thing because the decaying DC component effect is suppressed after n/2 cycles, while the Rosolovsky and Shane, due to its recursive nature, what I mean by that is that they use past samples. They require n/2 plus 1 and n/2 plus 2. And our algorithm is as fast as Rosolovsky and Shane, even with additional delay due to the filtering requires on decimation process. I didn't mention that because we kind of have low time here, but due to the decimation process, you have to apply filtering before you do the decimation process. And even with that, we still have a fast response. And, yeah, thank you.
Okay, questions for Tiago? Everybody's tired, I guess. The inclusion of the Butterworth filter delayed your process, but it was not a problem. Is there any problem compared to the other two methods?
Well, as we could see, I mean, it doesn't have the fastest rise time, if you will, in the simulations, but because it has a very smooth response, at the end of it, it's pretty fast.
Have you published this in journal paper?
Can I? Professor Kleber wanna say? They have published a full cycle one, a full cycle version of that. Basically.
Excuse me? Can you repeat?
Professor Kleber has published a full cycle version.
The full cycle.
Yes.
Okay.
It's pretty similar formulation.
Isn't the oven yet? It's still in this one. No, this one. This is in the oven, right? Yeah. Okay. Any other question? Okay. Let's give another round of applause to Tiago. And with this presentation, the first day of the workshop comes to its conclusion. On behalf of the organizing committee, I'd like to thank all the invited speakers, all the paper authors, and I think we see you all together tomorrow at 9? At 9 o'clock. Thank you. Let's finish the day.